Okay, guys. Um, I'm hearing an echo. I think I've got too many things open. Let's go back here. Hello, everybody there?
I'm here.
Okay. I am getting a definite echo. Hang on, guys.
It looks like you're joined twice, Dr. McDonald.
I'm sorry.
It looks like you're joined in twice. Like there's two screens for you.
Yeah, that's what I'm trying to get rid of one of them.
Mm.
Okay. One of me now?
Yes, sir. There's only one of you.
That's good. The world can't take too many of me at one time. That's just too much. Okay, guys, I got the PowerPoints. You tell me what you want to talk about.
Dr. McDonald, it looks like you made me the host and you made yourself a co-host.
Well, aren't I sweet to do that? Oh well, it makes no difference, guys. We're recording this for those folks who can't be here. Let me make sure. Yeah, we're still recording. Okay, guys, um, what's on your mind? See if I can turn this sound up a little higher.
Is with the all the different kinds of bonds, um, is
Yep.
there like a trick to remembering all the different ones?
Yeah, here it is.
Okay.
So, ion, they take it away, just outright steal it. It's gone. And then we can share. We can share evenly or we can share unevenly. That's pretty much all it. The hydrogen bonds are a little bit different, but they're more like just electrical attraction. They're very weak, although they're very important. How's that? Is that
Good.
helping a little?
A little, yeah, for sure, especially with the ionic.
Yeah, I mean, porosodium's got one in its outer shell. It does not have any chance in this world of getting seven more. The
Right.
best thing for this guy to do is let's just get rid of it, and he's happy. Is that his next shell has eight? Of course, now he has one more proton than electron, so he's going to be +1. And in the chlorine that had 7 in its shell, took sodiums. He's stable, but now again they have one more electron than proton, so they're negative. Positive, negative attract. How's that?
Yeah. I think the other
And
thing is with like the covalent bonds, is it just essentially about how many
sure.
electrons that it's sharing with like the nonpolar and the double and the triple?
No, it's really about who's got more pulling power, and some of it. I know everybody hates this word. Is about the geometry. So you've got carbon dioxide. Oxygen has 6 protons in its nucleus. That's a lot more pulling power than carbon's 4, right? But the way it's situated is the carbon is in the middle and the oxygens are on opposite sides. So they're both pulling equally, so they don't actually manage to pull anything. How's that?
Yeah, that
That's it.
yes.
That's it. Now, the uneven, the polar, you've got hydrogen, but instead of being on opposite sides, they're kind of bent like this. So oxygen's got 6 protons to pull with, hydrogen has got 1. So the electron goes closer to oxygen than it does hydrogen. Now, it's not a full -1 or +1, but it's a partial charge. And that's what gives rise to those hydrogen bonds.
Okay. That makes sense. Thank you.
My pleasure, ma'am. What else, guys? And for you guys that maybe aren't in class every day, this is only going to cover chapters 1, 2, and 3. The tissues are not going to be on this test.
Okay. And is it still on Tuesday?
Yes, ma'am. I think,
Okay.
is that what we said, guys, when we were in the class? I think we did. I don't have the schedule in front of me. Well, I can look. Let me look real quick, guys, since it's right in here in this same thing. Let's see. Yeah, it has
Can you
to be
see
on
the chat?
Tuesday. It has to be on Tuesday because Thursday is actually a holiday. It's Juneteenth, and we're not going to have class
Oh,
or anything. So
okay,
yeah,
perfect. Thank you.
that's why I had to slice off one chapter because we just couldn't get to it.
Okay, great. Thank
What
you.
else, guys? What else can I tell you? We got lots and lots of time, so you just take your time and look and see what you want to see. See if I've got any questions.
Can you see the chat, Dr. McDonald?
Hang on just a second.
Okay.
I'm looking to check and see if anybody in the emails have sent us any questions because I told them I'd cover them.
Um, Eliza said that, do you mind just going over the chemistry PowerPoint?
The whole
And going over,
power. Oh
she
God.
said go over the chemistry PowerPoint and go over exactly what we should know for the test. And then everybody else agreed
That
in
is
the
the
chat.
chemistry PowerPoint.
I feel like that is definitely the one that gives me the most trouble too. Like,
Well, sure. I mean, it does for everybody, guys.
right.
But um, I'll do it. But this is a bad time to be reviewing it from the very get-go. Let me pull that down and open this up. Well, I better not do that. I'll just do it like this so I can draw. Okay. Now, let me share this with you guys so you can see it too. Okay, guys, can y'all see that? Chapter 2?
Yes, sir.
Okay, well, let's go through. Kinetic energy, potential, that's just definition. Kinetic energy is the energy that's moving. And if you take a battery, you got two poles, a positive and a negative. While it's in there and just stored, that's going to be potential energy. But as soon as you hook it up to something like your cell phone, then those electrons are going to start moving, and then that's going to be kinetic energy. Now, these can fall into either of those categories. So the type of energy we deal with is chemical energy, which is the battery, electrical, which is the moving particles, mechanical energy, which again is moving like a vehicle or something like that. That's mechanical energy. And then we have the electromagnetic. That's things like light and ultraviolet, X-rays, even heat would be a radiant form of energy. If you've ever stood in front of a fireplace or whatever, you know you can feel the heat. The heat is moving, and it's definitely a form of energy. This is pretty easy. Hopefully, you guys have at least heard about this before. The law of conservation of energy says we can't make or destroy energy. We can just change it from one form to another. So the mechanical energy of water falling through a dam, going through the turbine, turning that, generating electricity. But here's the key thing. A good percentage of it is going to be lost as heat. Once it changes into heat, we really don't have a whole lot to do to recover that. So that's just a one-off. Periodic table is classified. Everything on this column right there has one electron in its outer shell. These guys have two, or sorry, this one has two there, but these also have two in their outer shell. Three all the way up through these guys, but don't worry about that. I'm not going to ask you anything on that. Here's what you need to know. The atomic number of, let's see, let's go back up here. There's carbon has got 6. Now I said carbon had 4 electrons, and it does, but if you remember, the first shell can only hold 2. So it has 4 electrons in its outermost shell. That's all the atomic number is. It's the number of protons. The number of protons does not change for all our practical purposes. The only way to change that is through nuclear reactions, and that's way beyond what we care about. So if you change that proton number, you've got a different element. It's not the same. Atomic symbol is just a shorthand way. A lot of these just make sense. Carbon is C, nitrogen is N. Sodium is Na, which is the Latin word for sodium. Don't worry about that. Just the atomic symbol is just usually 1 or 2. So I think they do have some 3s now. The atomic weight, okay, there's hydrogen with his 1 electron, 1 proton. That's probably about 98% of all hydrogen. But you have a hydrogen that has 2 neutrons with it and still just has a single electron. And then, oh, I'm sorry, it should have been 1 right there, 2 right there. Those are called isotopes. An isotope just means that it has more than the normal number of neutrons. Usually these guys are radioactive and they break down. So with carbon, we've got a carbon 12, we've got a carbon 13. So that means this guy has 6 protons and 6 neutrons. That's the majority. This guy's going to have 6 protons because that's what makes it carbon, and 7 neutrons. Carbon 14, the guy they use to date dinosaur bones, that has 6 protons and 8 neutrons. And those things break down at a certain rate. That's how they can use it for timing. But the atomic weight, so if this is 90%, no, let's just call that 95. We'll say 95% of all carbon is 12. And maybe 4% is carbon 13. That means that 1% is going to be carbon 14. So what they do is they take those weights. So that's going to be 12. 6 and 7 is 13. That's where we got it right there. And then 14. They take all those weights, multiply them by the percentage of the carbon that it is, and that's how they come up with this funky number. Guys, you don't need to know all that. I'm just telling you is to kind of give you an idea to make it easier to remember. Sometimes if you understand things a little bit, it makes it easier to remember than just trying to memorize facts that don't mean anything. Anyway, that's the atomic weight. It's the average of all of the isotopes. So 95 times 12, 4% times 13, 1% times 14. Take all 3 of those and divide by 3. Okay, this is the way nuclear atom probably truly is, and we don't care. That's physics. For us in A&P, this works fine. There's the 2 protons. That's what makes it helium. This guy happens to have 2 neutrons. That's good. It's an even number. And he has 2 electrons. They call this the planetary model because it's almost like these electrons are like little solar systems with them orbiting the nucleus like a planet does the sun. But we'll just use this because it's all we need for the kind of stuff we're interested in. Neutron has no charge, but it's the same size as a proton. A proton has a +1 charge. The electrons are around the nucleus. You usually, that's what we need to say, usually have the same number of electrons as you do protons. These guys have a negative charge. These things, it takes 2,000 of these to equal 1 proton. So for all practical purposes, they weigh nothing. So if we had carbon 12, 6 neutrons, 6 protons, 6 and 6 is 12. That's its atomic weight. Here's what I tried to draw not so well. This is the main form of hydrogen. This is the heavy water that they were using to develop nuclear weapons in the 1940s. Deuterium and tritium. I think they used those for some fluorescent clock hands too at some point. But some guy bought a lot of old clocks and scraped off all of this, and actually was on the verge of making an atomic bomb when the FBI found it and confiscated it. I'm glad he didn't. Okay, the isotopes, radioisotopes, that just means they're radioactive. These guys are just going to break down. They're going to act, as far as the acting of chemical, it's going to be similar to that, because all that matters in chemistry is what's on the outside. So this guy has got 2 on the inside. That's full. This is what matters, is what's on the outside. I think that's boron. I'm not sure. We use radiation for cancer treatment, and that's really all we need to go with. We don't get too far. So this outer shell is called the valence shell. The first shell, if it has 2 in it, is completely full and is completely stable. That's why helium doesn't burn up like hydrogen. It's stable. It doesn't need anything. But as soon as you go to that third one, which is lithium, then you've got 1. Lithium is going to try to get rid of that and turn into a negative ion. Carbon, we've already seen. The 4 in the outer shell, that's all that matters. These guys are not going to have anything to do with how they bond. And it doesn't matter whether that's carbon 12, 13, or 14, same thing. Neon is, they call them noble gases. 2, 4, 6, 8. They are perfectly stable. This guy is not going to react. He's already where he wants to be. He doesn't need to react. Okay, elements. We can't break down an element under normal circumstances. You have to do nuclear stuff. Now, the physical properties of an element, you guys can tell the difference between a piece of carbon or charcoal and a piece of iron. The properties of these guys are different, and we can detect them, and you can measure certain things about them. But the chemical properties is all we're concerned about right now, and that's how we make bonds. There's our hydrogen, helium, there's that lithium we were talking about. What's in the outer shell? This guy is going to be highly reactive, so much so that he blows up. This guy is going to be very reactive. He's going to want to form an ionic bond, because he needs 8 for that. It's just not reasonable for him to get 8. Could this guy get an extra electron? I guess he could, but he's only got 1 proton to pull with, so that doesn't happen very often. Okay, oops, sorry, I just jumped right over that. Let me get back there. Okay, so atoms are going to really come into play when they bond with another one. So there's oxygen that has 6 electrons in the outer shell. He needs 2. Well, you know what? There's another oxygen. He's got 2 that he needs. So what they do is they share two pairs of electrons with each other. And that's going to be molecular oxygen, the stuff that we breathe in. It's double bonded because they share 2 pairs. That's a molecule. Now, having said that, this guy is a molecule too. Carbon dioxide, what we breathe out. We already talked about how these aren't polar because they're pulling. But the same thing, remember carbon's got 4 electrons, oxygen, so carbon needs 4 and oxygen needs 2. So he shares 2 pairs of electrons with this oxygen and 2 with that, and they're happy. So that is absolutely a molecule. Now, there are certain kinds of molecules, and to be this kind of molecule called a compound, it has to be different atoms. So this is a compound, that's not. Hydrogen forms molecular bonds with each other. That's not a compound because it's the same atom. To be a compound, you have to have different atoms that bond together. Okay, mixtures, physically mixed in. These are not bonded chemically. The atoms are not bonded together. These guys just happen to be in the same place at the same time. Salt water is a mixture, or if you put sugar in a bag, or put salt in a bag of sugar, that's a mixture. They're physically mixed in together, but they're not bonded. Could you separate them? Yeah, if you got a lot of time on your hands and not much of a life, you sure can. Now, our mixtures are going to be homogeneous or heterogeneous. Homogeneous just means that it's evenly spaced. So you get a glass of water and you put some salt and you stir it up. That salt, I know it's going to be broke down, but for right now, is going to be evenly distributed. That's homogeneous. Heterogeneous, you put something in there. Say I put too much salt, it's all going to fall down to the bottom, even if I stir it up because it's too much. That's heterogeneous. It means it's not evenly spaced. It doesn't have to be all clumped in one place, but it's just not spaced out. Okay, we got 3 types of mixtures: solutions, colloids, and suspensions. We'll take these one at a time. Well, you guys can look at that. That's not. You can separate a mixture, but you got to break a bond to separate a compound. Compounds are always homogeneous because they're always going to be bound the same way. Okay, solutions. You've got a solvent and a solute. Well, water's the best solvent we have, so water's always the solvent. Not really, doesn't have to be. Normally, when I drew you a little picture, I showed putting a teaspoon of salt in a glass of water. Well, there's more water than there is salt. So water is the solvent there, and salt is the solute. But what if I put a drop of water in a salt shaker? Then salt is the solvent and water is the solute. So whatever you got the most of is going to be the solvent, and whatever you got the least of is the solute. Okay. Sometimes they'll do this as a percentage or parts per 100. Milligrams per deciliter is the way we measure blood sugar. So if your glucose comes back as 100, that means for every 1/10 of a liter of fluid, you have 100 milligrams of sugar. That's all that means. Molarity is moles per liter. That doesn't mean that you have a liter. It just means that in a liter, this is how much you would have. A mole. A mole, if you have 6.02 times 10 with 23 zeros, that's Avogadro's number. Let me give you a good example. If I have 12 grams of carbon That's 1 mole. So what you do is you take the atomic weight, you change it to grams, and that's how much a mole is. So if you had 12 grams of carbon, you're going to have this many molecules of carbon in there. On the other hand, if you got 1 mole of hydrogen gas, you're going to have like 1.0 something grams. So a mole is the atomic weight in grams, that much. Okay, solutions we're done with. We'll talk a little bit more about this. Colloids, sometimes you hear it called an emulsion. It's heterogeneous. They're not all equally spaced. Translucent, not totally opaque, but you can sort of kind of see through it, kind of like those shower doors that are kind of frosted and so forth. Large solute particles, but they don't fall to the bottom. These guys can turn from a solid or solution into a gel. The cytosol in our cells are a good example of those. Suspensions, they're heterogeneous, and the main solutes are going to fall to the bottom. Now, in our blood, that doesn't happen because the heart's moving it. It's being pushed. But like I was telling the folks in the class, if your heart stops, then all that blood, those red cells and everything are just going to fall to the lowest part of your body within your blood vessels. Solutions you see through, they're clear. Colloids, they're kind of more or less, you can maybe see through a little bit, and Jello is a good example of that. A solute is the particles are very large and they definitely going to fall. These guys have large particles, but they don't settle in one place like blood does. Okay. The octet rule, this is another definition things. Guys, that's just what I was telling you. Everybody wants 8 in their outer shell except for helium. He's happy with 2. But everybody else needs 8. Well, hydrogen can be happy with 2 as well. Okay. But that's the octet. Hydrogen, carbon, oxygen, sodium. They're just showing you some pictures. Ionic bond we talked about, the polar and then the nonpolar. And that little symbol right there just means it's got a partial charge. I believe that's going to be a Greek delta. Jump again. Okay, here's some more definition, guys. So the guy who gets rid of the electron is going to have 1 more proton than he does electrons, so he's no longer neutral. He's going to be charged positively. So let's see. Sodium, I'm thinking, let's see. Sodium has 11, I believe. So sodium has 11 protons and 11 electrons. But that last electron is in that shell all by itself. So he loses that. Now he's got 10 electrons and 11 protons. So if I've got 11 pluses and 10 negatives, you add them together, you got 1 plus. That guy's called a cation. Now, the one who gets it has 1 more electron than they do protons, and those are called anions. A negative ion. That's the mnemonic. So if you remember that, then the cation is just the opposite. Ionic compounds, we'll see this in the slide coming up. These guys don't actually form molecules, they kind of form crystals. There's the sodium and the chlorine. There's the sodium, who's now a +1. The chlorine is a -1. They're attracted to each other and they form crystals. There's the big chlorine and the small sodium. You see how these guys are surrounded on all sides by the opposite charge. And they stick together. You've got salt crystals in your salt shaker at home. They can be broken, or not broken, they can be moved apart. Covalent. Atoms do covalent bonding when they smash together, literally. They run into each other, and when they run into each other, then they start sharing electrons. If you've ever had a chemistry class, the first thing you do is you turn on heat. Why? Heat. That heat energy makes the molecules in the substance move faster, and the faster you go, the easier it is to have a wreck. And that's exactly what we're doing. So we're going to share electrons. Can be equal or unequal. We talked about that. We don't need to go into that again. Okay, electronegative, electropositive. If you got 6 or 7 in your outer shell, then you're electronegative. In other words, you tend to grab electrons rather than get rid of them. It makes sense. If you got 6, it's easier to grab 2 than it is to lose 6. And it's even worse with if you've got 7. But if you've only got 1 or 2 in the outer one, it's going to be easier to get rid of those than it is to get all the way to 8. So those hydrogens bump into that carbon and they share 1 pair each. So the 4 carbon electrons are each shared 1 by 1 with the hydrogens. And then you got methane. Oxygen and oxygen, we already talked about the molecular oxygen. Nitrogen has got 5 in its outer shell. So this guy has to share 3 pairs with each other. And that's what he get this structural formula. And that's the atmospheric nitrogen that we have all around us. Talked about the polar bonds. And it's just oxygen has more pulling power. Hydrogen bonds, this is super important. Even though these are the weakest bonds, these guys are everywhere. So that partial positive and that I'm doing wrong, opposite. Partial positive and partial negative are going to attract each other. That's what gives water the ability to come just barely over the lip of a glass. That's what lets those striders that walk on the lakes, they are not breaking the surface tension because they're so light that they can't even break these bonds, so they can basically walk on water. Okay. We'll talk a little bit more about that coming up. Chemical reactions. We make bonds, we rearrange, or we break them. That's a reaction. Something happens. So what we do is it's almost like an equation. You put what you're starting with on one side, put what you wind up with on the other, and it should be balanced. If I've got 2 hydrogens there, then I got to have 2 here. This guy's got 4 hydrogens and 1 carbon. 1 carbon, 4 hydrogens. The equation always has to balance. Synthesis, decomposition, and exchange. A and B run into each other and then they bond. That's it. Decomposition, for some reason, this molecule breaks apart. Exchange reaction, A and B are going to collide with C, C is going to actually make A more stable than B does. So A is going to grab C and release B. Synthesis, you make stuff. Okay, there is 1, 2, 3, 4 hydrogens and 2 oxygens. Those oxygens are going to break apart from each other, and each one of those oxygens is going to grab 2 hydrogens, and then you got the water. Synthesis, also called anabolic, making stuff. There's 2 times 2, that's going to be 4. 2 times 1 is 2 of those. 2 times 2 is 4. And 2 times 1 is 2. So that equation balances out. Decomposition, we're breaking stuff. That's hydrogen peroxide. H2O2, that is totally unstable. That's why they keep peroxide in those brown bottles. Those things, you're gonna start with 2 of those. They're going to break down, and they're basically going to break down into 2 waters and just oxygen gas, O2. 2 times 2 is 4. 2 times 2 is 4. 2 times 1 is 2. And then 2 times 1 is 2. So I started with 4 oxygens, those red ones, and I started with 4 hydrogens. 1, 2, 3, 4 oxygen. 1, 2, 3, 4 hydrogens. Decomposition. Oh, that's not decomposition. That's a replacement reaction. They got that labeled wrong. This is exchange or replacement operation. And again, it's just when this guy can get more stable by releasing that. So there's blood sugar and there's ATP. So once this guy gets inside the cell, ATP is going to drop one of his phosphates and it's going to attach to that. That's going to keep it from floating out of the cell. This guy's going to go down to ADP because he's only going to have 2 phosphates. Thing about it, those phosphate groups are negative charge. And if you take a negative and a negative and a negative, and you jam these guys together, that's very unnatural. That's why when you break those, you release a lot of energy. Redox. This is where something is going to exchange. This is not ionic bond, guys. Don't want to give you that idea. But these guys pick up electrons. Now, this guy is being oxidized, and that means he's losing these electrons. He starts with 2, he loses them, and then he's good. This guy is going to be reduced. He's going to start with no extra electrons, going to wind up with 2. Now, a lot of times when we get to this later on, this guy's actually going to take an entire hydrogen. So when we say electron, we mean a hydrogen, and so he's going to have a proton and an electron. But that's something that's really important in the way we break down sugar to make ATP. Exergonic, endergonic. Exergonic is going to be any catabolic. Catabolic is the same as decomposition. When you break a bond, you release energy. Endergonic is going to be anabolic. To put 2 things together, A and B, you have to have energy. And I just got finished telling you that a lot of times that's what happens in the chemistry class. You heat it up so that these guys have enough speed. They're moving so fast, they're going to collide, and you're going to get the reaction you want. Equilibrium we've already talked about. No, we haven't. I'm sorry. So here's the thing. Most chemical reactions can go either way. So like this guy, this A plus B equals AB. Well, here's the thing. Most of the time, it can go either way. The AB can break down into A plus B, or the A and B can come together and form uh, the AB. Which these equilibriums are not 50-50, guys. They can be 80-20, 90-10. It just depends on the exact chemicals you're talking about. Now, in biology, in what we're concerned about, a lot of them are basically not going to be reversible because some of these may take energy, and energy is not available for it. The other thing is these guys, if we make this guy like this and he starts to float away, he's no longer in that area, so he may not be able to break apart. Or if you've got coming this way, A may go over here and B go over there, and that's going to make it almost impossible for them to get together. There are some that are reversible, but a lot of them aren't. In equilibrium, we'll talk more about that when we get into acid base. Okay. If you want the reaction to go fast, here's what you need. You need more temperature. We said that. The faster the car goes, the more chance it has of hitting another car. Particle size, the smaller it is, the more chance, the faster the reaction. Why is that? Well, if I put a 454 engine in a diesel truck and I put it in a little sports car, I'm going to get more speed out of the sports car because it's smaller. The engine can turn more of that energy into speed. So the bigger a particle is, the slower it's going to go, even with that energy added. The other thing that's going to increase the rate is how many you got. I told the folks in the class that if you go out to Montana, you've got 85 miles an hour speed limits on the interstates. That's because there's no cars around. There is antelope and there's elk and P-dogs. That's about it. But if you were to go fast and be in a small sports car and you were down in Cobb County, you got a good shot at having it. So the more there is in the area, the more likely they are to bump into each other. And that really should make, just kind of common sense. Sorry, guys. Catalyst. Catalysts will speed up a reaction, but they themselves won't be changed. And the catalysts that we use are called enzymes. So here's these two guys. So this guy bonds with this guy. He's attractive. This guy bonds with this part. Well, they're very close together, so they manage to have a collision at a very slow speed, and they get released. They're bound together. The enzyme hasn't changed a bit. So we say with an enzyme, you can get that reaction and use a lot less energy because they're closer together. Without an enzyme, it takes a lot of energy. And all the chemical reactions that the enzymes in our body do would happen anyway. But it may take 5,000 or 10,000 years, which we don't have that much time to wait for them. Organic and inorganic. Inorganic is going to have carbon and hydrogen. It's got to have both. Methane is organic. It can have other stuff. This is glucose. C6H12. It's organic. H2O. Well, it's got hydrogen but no carbon, so it's not organic. This has carbon but no hydrogen, so CO2 is not organic. HCl has hydrogen but no carbon, and it's not organic. Most of our body is composed of these four things. This is what you really need to know. Carbon, oxygen, hydrogen, and nitrogen. That's most of our bodies. If you look at these percentages, let's see. That's 19 and 9 is 28. 28, 65 is 90. It's like 93% of our body is composed of this. And of course, most of our body, we use this in the form of water. We have these other guys in here, and we even have trace elements. We need these, but not a lot of them. Chromium, copper, we need this. Iodine, iron, oh yeah, molybdenum, selenium, silicon, vanadium. That's what they coat mechanics tools with. Water, depending on the person, it's about the same percentage of our body as water is the same percentage of the earth is water. It's really strange, but that's one of those things. It's the most important compound in our body, the inorganic. Now, these things are easy to confuse, so let me spend just a second on them. High heat capacity. Water will absorb a lot of heat before it changes temperature. Now, if you get your favorite soft drink and you put ice cubes in it, until that ice cube is completely melted, that glass will stay at 32 degrees F or 0C. That temperature will not change until that's all melted. So here's what we can say about water. It will absorb and release heat without a lot of temperature change. We can't live with big swings in temperature. If it gets too hot, we die, and if it gets too cold, we die. So by having most of our body being water, it actually kind of keeps us from having these wild swings. And that's compatible with life. High heat of vaporization. So when we sweat, most of the time we never see those droplets. Those things get to the top of the pore and then they're gone. Now, if it's really humid outside, in other words, a lot of water is already in the air, then you're going to get those droplets of sweat. And as that thing that gradually evaporates, it's sucking heat from your body. So you get a kettle of water or a tea kettle or whatever, you put it on the stovetop, you turn that thing on full blast, it's going to take a while. All of that heat energy, it's going to take a while before you start seeing bubbling and steam come up. That's why we use this as our main way of cooling rather than panning like our dogs do. Because we can dump a whole heap of heat by this. So the high heat capacity is about keeping the temperature within ranges up and down. High heat of vaporization is about sucking heat out of our body when we're too hot, like in, say, August. Okay. So let's do this. Here's sodium. There's chlorine. Put it in water. This guy's a plus, this guy's a negative. So all of those hydrogens from those water molecules are going to surround that chlorine. All of the oxygens from water are going to surround sodium. and they're actually going to be pulled apart. That crystal is going to dissolve in the water. Okay, hydrolysis and dehydration synthesis. We're going to talk about that. But water, since oxygen and hydrogen are very reactive, they help us with some of this, and we're about to talk about this on the next slide. Cushioning, water, it has a cushioning effect, and we use that to protect our brain. Okay, here's the thing. If you call that an amino acid, if you call that a sugar, like glucose, if you call that a nucleotide, if you call that a lipid, all of these guys, here's what's going to happen. Here's A, and A has got OH on the side. Very, very common. There's another A, and he has a OH too. This is the way we do most of the chemistry in our body. We have an enzyme because this thing's not going to happen by itself. That enzyme is going to cause these guys to break apart and become water. Okay, so then we've got this A with an O that needs another bond. We have this guy that needs a bond, so they come together. That's called dehydration synthesis. It's synthesis because you're hooking things together. It's dehydration because you do it by removing water. That's it. That's the way we make proteins. That's the way we make lipids. That's the way we make DNA, RNA. That's the way we store sugar as glycogen. This is everywhere. This is worth remembering. Okay, so I've got to say this is glucose, and I've stored it in my liver, and it's late at night. It's been a long time since I ate. I need to break this apart so it can get in the blood and keep my cells going. What do? I bring the water back, and using that same enzyme, I'm going to put it back where it was. And then these guys are going to go and be used. That's called hydrolysis. Lysis means breaking. So you put water back and it breaks it back into its individual components. It's like a bunch of Legos. You can take the Legos, put them together, and then you can break them apart. Okay. We talked about organic things in living, but there are some organic compounds that aren't associated with living things. The type of organic compounds that we are dealing with, carbohydrates, that's just chains of sugar. Lipids are fats, and fats are nothing but a bunch of carbons with a lot of hydrogens and some oxygens. Proteins are amino acids. We'll have to see those in just a minute. Nucleic acid is what makes up our DNA and some of our RNA. Polymers is just, it's like if you had, say you got a yellow Lego and it's just a rectangle, that's a monomer, and you put them all together and they're exactly alike. You get this big long chain of exactly the same thing just connected together. That's a polymer. And we've already said that's exactly the way they work. Okay. We know carbon does the 4 bonds. There's one each. There's carbon bonding to another carbon with 3 of its 4 hydrogen or electrons, and then bonding with hydrogen with the other 2. So carbon can have single bonds, double bonds, triple bonds. There, you see this all the time. These are some common groups that you find on the stuff that we deal with inside. That OH, that's called a hydroxyl group. COOH is called a carboxyl. That COOH right down here will a lot of times lose that hydrogen. So this guy is actually an organic acid. An amino group is a nitrogen with 2 or even 3 hydrogens. Methyl group is methane minus 1 hydrogen, because if it's going to be on another molecule, then it has to have at least 1 bonding space. Phosphate, which is what we were talking about, is PO4, and this guy has a -2 charge. That's going to be important. Oh, I'm sorry, I jumped the gun right there. Oh. Monomers, polymers, we've already talked about. We've talked about those. Sugars and starches. Sugars come in 3 forms. There's monosaccharides. That's just a single sugar molecule. They can be 5-sided or 6-sided or even whatever. These guys are always going to be like this. For every carbon, you're going to have 2 oxygens, and you're going to have 2 hydrogens and 1 oxygen. So glucose is C6. This formula, H should be 12, and oxygen should be 6. And so it is. A disaccharide is when you get 2 sugars together and bonded. Sucrose, table sugar, is a combination of glucose and fructose. Lactose, milk sugar, is glucose and galactose. And let's see, we said sucrose. Oh, maltose, what you get in your milkshakes, are 2 glucoses bonded together. So that's the disaccharides. Polysaccharides, these are going to be long chains. That's going to be your carbohydrates. That's going to be starch, which you get from plants, and glycogen that you get from animals. Glucose is our primary source of fuel. And some of those, like those 5-sided, we actually don't use those for fuel. We use them as building blocks. Kind of interesting. So there's glucose and fructose and galactose. These are fuels, and if you bound these guys together, you make those different disaccharides. This is what we use to make DNA and RNA. The difference between these two is this one has no oxygen there, and this one does. That's deoxyribose, that's for DNA, ribose, that's for RNA. There's our sucrose, the sugar you put in your coffee, maltose in your milkshake, lactose, milk sugar, which a lot of folks don't have the enzyme to break that apart. Did you guys notice that these guys are connected by a bond with an oxygen in the middle? Exactly. Just like we said. Here's glycogen. This is what we do. If we have excess glucose, we will chain it together, dehydration synthesis, you see the oxygens, in our liver, and then late at night, maybe at 2 or 3 in the morning, when our blood sugar is going down because it's been like 8 hours since we've eaten, then the liver will break these apart, hydrolysis, and release these guys into the blood so that our blood sugar doesn't drop. You don't want to go into hypoglycemia in the middle of the night. These are amino acids. This is what they look like. There's the amine group. And there's the COOH, the carboxyl group, which is what makes it an acid. So there's 20 amino acids that we use. They all are going to have that amino group. They're all going to have this carboxyl group. They're going to have a carbon with a hydrogen. And then what in the world is an R? An R is the same as a blank box. It just means something attaches here. This guy attaches a hydrogen there. He's the simplest, glycine. Aspartate has a CH2 and another COOH group. Lysine has a much longer, and this guy, cysteine, even has sulfur on it. These are what proteins are made of. We just do exactly what we said. See the OH and the H. Those guys are going to form water. And there's these guys going, now in this case, we don't have an oxygen in the middle because there's no oxygen on that amine group. So that carbon right here is just going to bind to the nitrogen on the other one. And that's a dipeptide. To break it apart, same thing. You add the water back in and it goes back. Dipeptide, tripeptide, you get 3 amino acids. That's about as far as they name them, guys. That's the biggest that we can take in our GI tract is a tripeptide. A polypeptide is just more than 3. And usually they don't call it a protein unless you got at least 50 amino acids. I usually just use protein, but whatever. Okay, here's protein. These guys are connected one to another, the carbon to the nitrogen, carbon to the nitrogen. That's it. So you get these guys and you just connect them, and they're sort of like beads on a string. That's the primary structure right there. Now, some of these guys are going to have charges in different places depending on what's on here. Because remember, there's all kinds of stuff that can go on there, at least 20 different things. Some of this might be a negative, this might be a positive, and the chain is going to bend around so they can get close together. And that's our secondary structure. So sometimes the chain will kind of spiral like this. And that's the alpha helix. Sometimes these guys are going to fold themselves like this, as looking at it from the side. And those dashed lines right there, those are the hydrogen bonds, guys. Partial charges coming together. Now, this is our tertiary structure. So that's going to be like a beta pleated sheet, and this is going to be alpha helix. And this is the thing, you can get a helix and then a sheet, maybe another sheet, another alpha helix. You could have that protein, that whole big long thing can have all of these different. But what's going to happen is, even after it folds like this, maybe this guy is attracted to this guy. Because of that, these guys are going to twist again. And that makes the tertiary structure of a protein. This is the last, and it's quaternary. Now, quaternary, this guy, this is as much as a single protein strand can do. He cannot do anything else. Tertiary is the limit. What about quaternary? Those are more than one protein structures that come together. Probably the most infamous of those are going to be hemoglobin. There are 4 different protein strands together. Some of our proteins we use as building blocks. Some of them are going to be actually functional, depending. Collagen is a protein, elastin, all of these things, and they don't dissolve in water because they are what holds us together, literally. Globular, these guys will dissolve in water. By dissolve, I don't mean split apart. I mean they can be surrounded by water. And these guys are going to be the enzymes, hormones, antibodies that we use to attack the bad guys. Denaturation just means if you've ever seen an egg fry, you know you can't unfry it. So if it's like cooking an egg is irreversible. If it's not very extreme, sometimes it can go back. Here's what happens when you denature a protein, it changes its structure. That's not always gonna work. So if you take your metal key and put it on a table and take a blowtorch and melt it down into a puddle of metal, well, you still got your key. It's probably not going to be able to go into your door or your car and break things up for you. So this is going to be, that's why if we run a fever too long, we're going to have some problems, because increased temperature, just like cooking an egg, can denature our proteins. We can also get this problem if we become too alkaline, or too acidic. We'll talk more about that. There's the same thing we saw, the way the enzymes lower the energy makes it possible. Go talk about enzymes. A lot of the enzymes that you hear about are going to end in ASE. So people who are lactose intolerant do not have lactase, the enzyme that breaks it up into galactose and glucose. So that means it doesn't get absorbed through the GI tract. It goes to the colon where the bacteria have a good time, and the person doesn't. An enzyme is usually going to be the protein part, but sometimes these guys need an extra thing. They can need a cofactor, which is going to be metal, or they could need a coenzyme, which is what we do with most of the vitamins that we need. Let's see. So the protein part is called the apoenzyme. If you have a metal ion, it's a cofactor. If it's a vitamin, it's going to be a coenzyme. A holoenzyme is, I lost my pen again. A holoenzyme is the name for the entire functional enzyme. Now, not all enzymes need an ion or a vitamin, but some of them do. So, some more definitions. The things that come together for the enzymes are called substrates. The place where they bind on the enzyme are called the active sites. So there they are together. The enzyme is going to help these guys, like do dehydration synthesis. When it's finished, these guys are going to break off and they're connected, and the enzyme's ready to do the next one. Lipids. Lipids, oil and water never mix. Why is that? Because water is attracted to each other, like we saw, because they're partial charge. Thank you. fats have no charge whatsoever, none. So that's why if you pour oil in water, it'll eventually, they'll settle out. The water and the oil will be on opposite sides of each other. They don't mix. These guys are going to have carbon and hydrogen and oxygen, but they're not going to be on that same CH2O as we saw with the sugars. Sometimes you even get a phosphate in there, a phosphorus group. So the phospholipids, steroids, icosanoids, or the neutral fats, or the triglycerides, we'll talk about those. This is the main way we store our extra calories that we get in our diet that we don't need for glycogen, that we don't need for running ourselves. We're not going to just throw that in the toilet because that's calories are hard to come by in this world. So, well, not for us, but for most living things, they're hard to come by. So we want to hang on to it. So a triglyceride, you're going to take a glycerol molecule and you're going to attach 3 fatty acids. I'm about to show you what those look like right now. There's glycerol, carbon, 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 hydrogens, and then there's the oxygen. Well, what do you know? That's an OH. There's 3 fatty acid chains, which has an oxygen there, and the OH, which again makes it an acid. And then the rest of this is just carbon, 2 hydrogens, carbons, 2 hydrogens, till you get to the end. So we're going to do dehydration synthesis, hook these guys together, and that's the triglycerides. That's the main form of lipid storage. Now, saturated, unsaturated, and trans fats. No doubt everybody's heard of that. Polyunsaturated. Saturated, if you look there, each one of those carbons is carrying the maximum hydrogens. This guy, the carboxyl group, I know it's a carbon, but these guys are basically saturated. That means they only have single bonds. Each carbon is making 4 bonds. That's what's like in butter. Unsaturated means you have a double bond in there. You could have more than 1 double bond. You have many double bonds in the chain itself. That's the polyunsaturated. You don't have as many hydrogens. This is going to be those plant oils, olive oil, things like that. Trans fats, these are the ones that are not really good for you. These guys are normally oils, but because of their rearrangement, they are actually going to become solids. By the way, guys, oil is a lipid that's liquid at room temperature. Fat is a lipid that is solid at room temperature. That's really definition. This guy, now see this bond right there, we don't want to get too much in the cis and the trans, but just this guy, this is going to be like in margarine and a lot of those other things. Trans fats are considered to be really, really bad for you. Phospholipids, you get glycerol, 2 fatty acids, and a phosphate. And let's go ahead and look at that. So there's glycerol. There is our 2 fatty acids. Now this one is going to have a double bond, so that, I don't know if you guys noticed, but saturated is straight, but when you get a double bond, it kinks. Come on now, I don't want your help. Well, that's pitiful, but that's all I can do. It also has on the touch to this guy phosphate group, which means it's got a charge. This, we'll talk more about this in cell if we have time. We're burning up a lot of time with this chemistry, but I'm guessing that's what you guys. Steroid. These guys are forming rings, but they're lipids. And basically what they do is they take cholesterol and you modify it some way. So there's cholesterol, you got these side chains, the hydroxyl, the methyl, another methyl, and you got this long chain right there, fatty acid probably. Well, I guess I'm going to be talking about this then. Carcinoids, these are like the prostaglandins. These guys are things that are used as signaling. Arachidonic acid is the thing that activates when we get hurt, and it actually starts a cascade of chemicals that results in a pain signal to the brain. We don't like pain for any reason, warning or any otherwise. So we take aspirin, which interferes with that. And if I'm not mistaken, I think it's this one right here, prostaglandin E. I can't remember whether it's 1 or 2. But aspirin interferes with arachidonic acids coming into there, and that keeps you from feeling the pain. Unfortunately, this guy is also involved in making that coating on the inside of our stomach that protects it from acid. So if you use too many of these guys or chronically, it can actually cause you to have a thin mucus coat and you burn yourself with your own stomach acid, and that's an ulcer. We still got a few more to go, guys, and I'm about to talk out. Nucleic acids, DNA, RNA, carbon, oxygen, hydrogen, nitrogen, and phosphate. Each of these building blocks of this guy is called a nucleotide. They're going to have a molecule that has nitrogen. They're going to have one of those sugars that we saw. And they're going to have a phosphate group. And here's the best way to look at that. Now, those exact same ones we saw. There's the DNA, no oxygen. Here are the bases. Adenine and guanine, these are double rings, but they've got nitrogen. Got nitrogen in several places. There's the phosphate group. So the phosphate group is going to attach to this guy. That should be the number 5 carbon. 1, 2, 3, 4, 5. And then on this guy, he's going to attach to one of these bases. Now, these two guys are in DNA and RNA. This is in DNA and RNA. And this one is in RNA, and this one is in DNA. I did that wrong. Sorry, guys. This is in RNA, and this one is in DNA. In DNA, A and T are going to hydrogen bond together. And C and G is going to hydrogen bond together. In RNA, A is going to hydrogen bond with U. That's the main difference between those. So the 3 differences between DNA and RNA is RNA is going to have that oxygen right there. He's going to have a different sugar, not much different. Adenine is going to bond with uracil here in RNA, but with thymine in DNA. And these guys, well, there's another difference, but let me see if we get in that. I think we'll get in that coming up. Here's the thing, guys. Remember those pairings. As a matter of fact, memorize them. you will get so much mileage out of this when it comes to questions. These guys hydrogen bond with each other. I don't think I've got a lot in here.
Hey, Dr. McDonald. I don't want you to
Yes.
waste your breath on this because it's just me and Eliza now, and I feel like we have a good grasp on
Oh,
the
thank you.
this stuff. Yeah, I got you because it's just me and her now. So I
Okay.
feel like as if I feel like I can speak for both of us when I say that this we have a really good grasp on
Okay.
from micro and whatnot.
Yeah.
But it was like the earlier stuff that was harder.
Okay. Oh, just the
For
basics. That's good.
Yeah, yeah,
That's
because I
good.
feel like as if we learned the hard part first, really, or
Oh,
retain the hard part first anyway.
yeah. If you get
It's
the
the
basics,
basic
the rest
stuff.
of this stuff kind of falls into place.
Right,
About one
exactly.
of the things that's really been difficult for people is those functional groups, especially
Yeah,
the ones that you're going to run into all the time. OH and the phosphate, they're all over the place.
yeah, they are. Yeah, for sure.
Okay. Anything else you guys are interested in?
Um, I feel like those are really that you hit everything that was I was a
That's
little
the one
confused on.
that
Yeah,
gets
yeah,
everybody.
yeah, yeah.
Okay.
I mean, chemistry just in general is not easy, so.
I don't think the high schools do a good job. I don't know. Maybe people don't take it. I don't know, but that's just been
Well,
something I've seen ever since I started teaching.
it's been
That's why I
15
generally,
years for me. So I'm like, I just need a refresher.
yeah, I usually get set aside 2 weeks with chemistry because I know it's going to be the biggest stumbling block for folks.
100%. Yeah. Yeah,
For the
it's been a
RNA,
long
you
time
want
since I
to,
took that.
okay, Eliza, look into tRNA or just stick with mRNA. Well, tRNA and mRNA and rRNA all work together in the ribosome to put together the proteins. That's going to be in chapter 3, though, but look over that if you have any trouble. And I tell you what I tell the guys in the class, go to YouTube, find an animation. This stuff is, it's so much easier to see when you see it actually happening in a good CGI. That's what I would do. And I actually played some for them, I think, last Thursday. So I'll be glad to tell you anything you want about it, but
No, thank you for
it's
that.
involved.
And then are there any chemicals or elements that you want us to memorize, like their atomic number and atomic mass, or are you going to provide us with that information?
About the only thing, you might get a question that asks you, what does the atomic number mean? What does that relate to? Number of
Okay.
protons. But no, you're not going to have to memorize like how many electrons are in an outer shell. I'll give you that if there's anything like that. Usually there isn't.
Okay, thank you so much. I think that's all the questions that I had, and I'll just review some more with your YouTube. But I think Sydney was right. It was mainly the beginning portion of the beginning and
Sure.
middle portion of your chemistry PowerPoint.
Well, I tell you
Mhm.
what, guys, if you do have any questions, just shoot me an email. We still got several days. I mean, we got the rest of today and Monday, and I'll be more than happy to help you with anything you guys have having you know sticking with you.
Thanks, Dr. McDonald. I really appreciate that.
Okay,
Yes, thank you so much.
I'm going to end this recording, and then I will